Right, good afternoon everyone. We'll start now. So we start with what we have done last week. What was the last thing we finished off last week? You were joining online, you took the notes down? Right, good. So we discussed aldehydes and ketones. Did we finish aldehydes and ketones off? No, we just started, right? Right, we just started. So today we will start with now these questions are the kind of questions that you need to know when we are starting aldehydes and ketones. We'll start with a small question. Right, so let's see if you are able to remember certain past content that we have studied before coming to this point. And as I always do, we'll start with that and then we'll move on to our lesson. So I expect you to, without any issue, very clearly remember basic conversions that we have done in the past. Like when it comes to alkanes, alkynes also, very little bit of alkyne equations also we learned. And then we learned about alcohols. Now we are in aldehydes and ketones. Right? Alkyl halides also we did, right? Alkyl halides also we completed. So we will start with a simple question, and then after that we'll move on to something a bit more advanced later on after finishing aldehydes, because after finishing aldehydes we only have few more parts to go. Most probably we'll be able to make good headway today. So we'll complete this conversion. Can you quickly tell me whether we have done this question? Can you quickly tell me whether we have done this question, this specific question? I would have given this to you. No, I haven't. If I haven't given this to you, please complete this question. Are you sure I haven't given this to you? All right, do this question. Done? Very good. Very good. Okay. So we have done one additional step, I would say. So now you did this to get a double bond here, right? Can you not get a double bond directly from here to here? Think. You're right, but like, why can't we get a double bond from here directly? Is there a way? Ethanolic KOH elimination reaction, right? Yeah, so we can do that. And then you are right here. Very good. Correct. Very good. Yes. Very good. Yes, you have done the first one. Okay. Right. Now, I don't think you are doing anything necessarily wrong up to this point. But when you do this, I can't say, because now if you're producing this and then trying to get here, it will not be possible. Now imagine when you are, this is addition of water molecule that happens, okay? So hydrogen goes to the place where there's more hydrogen goes here, OH goes here. So since where OH goes is this one, carbon oxygen double bond will be produced here. Do you understand? It will not come to this corner. So that pathway is not going to be very feasible, right? Can I see? Very good. Yes. Exactly. Correct. Now, do you all get the feel of what needs to be done here, right? So let me see. Just getting you warmed up here. I just want to see whether you all are exactly correct. So then you need to remember these things. Now, for example, if I need to produce a aldehyde here, you need to have a alcohol group here. It will be the easiest way. If you have the alcohol or OH group here, it will be the easiest. And then from here, if you had something called pyridinium chlorochromate, PCC, right? Pyridinium chlorochromate, PCC, then you go to this. Now, how do you produce the alcohol here? Starting from here. So I need the OH group here. So then to switch the position of the OH groups, first of all, we can make a double bond here. We can do that easily by adding ethanolic KOH, and then you get CH3 CH2 here, and then after that we can add some HBr in the presence of a peroxide, right? We say we had CH3 OCH3, so this is organic peroxide. So then you are producing this CH3 CH2. So hydrogen goes here due to antimarconics, Br goes here. Then we can convert this using sodium hydroxide aqueous. So then you have a primary alcohol. Once the primary alcohol is produced, you can use PCC to get a aldehyde. Is that clear? So you should be able to get to these kind of answers without any issue, everyone. So that is something that we expect you to do, right? So actually aldehydes and ketones, they are filled with very interesting reactions, very interesting ones. So I'm not going to be able to, I will summarize it at the end, but I'm not going to be able to summarize it in the beginning, because each reaction that we are going to be learning here under aldehydes and ketones are not just a single type. All, like for example, very first one, we talk about addition of cyanide. So cyanide addition is a simple nucleophilic nucleophilic addition reaction. But after that, the cyanide group can be converted into carboxylic acid group. So that's another additional section. I can't just like cram it into a summarized version without properly explaining and giving you a note on it. Then after that we talk about Grignard's reagent, MgBr. MgBr also can react with aldehydes and ketones very well. So they also produce different types of substances, mainly different types of alcohols will be produced through MgBr reactions. Very nice reaction set, you will also see that here. And then we come across something called aldol condensation, or we say self-condensation of aldehydes and ketones. Self-condensation of aldehydes and ketones. Again, this one is, when you are taking it down, put with few stars, because this one helps increasing the length of a carbon chain. Right, you have one carbon chain with, let's say, 2 carbon atoms. If you want to make it 4 carbon atoms long, we use this kind of reactions, self-condensation or aldol condensation. Is that clear? So all these reactions are very interesting ones, like not just like a simple one that I can represent in a basic summary. We'll do that towards the end. Okay, after you know everything, then I can nicely put them together in a summary. Right, so last week I don't think we gave any reactions after talking about aldehydes and ketones. I didn't talk about any reactions, right? So take the first reaction. You can write nucleophilic addition reactions. That's the first one. Nucleophilic addition reactions. Under that first one, HCN addition. Is it warm to you? You all feel warm? Right. It's warm and it's difficult, no? But for you all at school, it would have been even more difficult. So under that, students, let's first understand what's happening here. If you take a aldehyde or a ketone, right? We'll take a aldehyde, but aldehydes and ketones both have this group. We have this carbon-oxygen double bond, right? Carbon-oxygen double bond is there. So that means the oxygen is partially negatively charged, whereas the carbon is partially positively charged. This is something that we already know about. So carbon is electron deficient here in aldehydes as well as in ketones, right? So because of that, if a nucleophilic group comes, any nucleophile for that matter, it will be able to donate electrons here and bond to and it can bond to the carbon directly. And then oxygen, I will show you the mechanism. For example, when you add HCN, we have Cn minus ions here. Cn, keep in mind, both carbon and nitrogen has a lone pair. Only carbon has a negative charge, right? If you take a look at HCN molecule, you have learned about this earlier. HCN molecule, it's like this. This is HCN. When H plus is removed from HCN, what happens is these bond electrons go here, producing H plus and Cn minus, producing H plus and Cn minus. There's a negative charge on the carbon. So this carbon will donate this lone pair to this carbon because it's partially positive, and we say carbon-oxygen bond here. Carbon-oxygen bond here, actually one of the pi bonds will break. One of the pi bonds will break. So now it is going to be attached there. And then you produce this CH3, CO. Now oxygen has 3 lone pairs. Earlier it had only 2. Whenever oxygen has a double bond, normally it has 2. I will attach the Cn group here, students, okay? I'll just write Cn and the hydrogen here. The reason why I'm writing Cn there is it's easier to show you the next step, right? So cyanide group attached just here. So we call this, after being attached, we call it a nitrile group. It's referred to as a nitrile, right? So and then this oxygen is now negatively charged. The medium will have H plus ions, so the negatively charged oxygen will donate a lone pair to form a bond between these two, resulting in finally producing something like this. We call this a cyanohydrin. We call this a cyanohydrin. Right, cyanide group is there, hydroxide group is there. It is referred to as a cyanohydrin. Is it understood? So this is the basic reaction that takes place. What's interesting about this reaction is, though that cyanide group is a fascinating group. It's like if you have a little bit of acid added to this molecule, the cyanide group quickly changes into a carboxylic acid group. That's an additional reaction. This is the basic normal reaction. Now, okay, this is nucleophilic addition reaction. Done. But we can have another use out of that. We can take this molecule. And add H plus and water. Then we can turn the CN group here into a carboxylic acid group. CN group can be turned into a carboxylic acid group. That's a separate reaction. Is that clear? Separate reaction. If you want, you can do it. If you don't want, you don't have to do it. So for example, now certain chemical reactions we want it to be in this form, so we do it then. Right? Certain reactions we don't want that, so we don't do it. Is that clear? Right. So can you please take this down? Do only the first one, don't write about the second one, do only the first one. After taking this down, please take a small note under that. Please take a small note under that. Write down, due to the partial positive charge on the carbon, due to the partial positive charge on the carbon, they can undergo nucleophilic addition reactions as shown above. They can undergo nucleophilic addition reactions as shown above. And the produced product is referred to as a cyanohydrin. due to the presence of a nitrile group, and the hydroxide group on the same molecule. Now students, by looking at this, there can be questions asked about, for example, they can ask you, in here, what is now cyanide group acting as? It is acting as what? Simple question. What is it acting as? What is it acting as? Nucleophile, not electrophile. It's a nucleophile. So there are only three types of things that usually we find. We find electrophiles, we find nucleophiles. What is the other one? Electrophiles are there, nucleophiles are there. What is the other one? Very first one we learned? Free radicals, right? So we have nucleophilic substitution, nucleophilic addition. We have electrophilic substitution, electrophilic addition. When it comes to free radical, normally we have free radical substitution reactions most of the time, right? Free radical substitution, but there are free radical additions ones as well, but very rare, right? So mainly free radical, nucleophilic and electrophilic mechanisms are seen. Reaction types are either addition or a substitution, right? Mechanism types are free radical, nucleophilic and electrophilic. There's something called reaction type. Reaction type happens to be either substitution or addition. Normally we put them together and say nucleophilic addition or nucleophilic substitution. Do you understand? So here this one is nucleophilic addition reaction. Understood? Right. Okay. So and then after that you can write the nitrile group. The nitrile group can be converted to a carboxylic acid group by the addition of an acid. Right, that's it. That's the very first nucleophilic substitution reaction, nucleophilic addition reaction you learn about. Then write the next one, reactions with Grignard reagent. Now Grignard reagent, we'll start with the overall reaction, okay? So write overall reaction. Now can you remember how the Grignard's reagent was formed? How did we form Grignard's reagent? Yes, we will take alkyl halide and you put magnesium in dry ether, right? So if you take alkyl bromide, let's say CH3Br, and to that if you add magnesium in dry ether, you produce CH3MgBr, which is known as a Grignard's reagent, right? That entire substance is now known as a Grignard's reagent. Now Grignard's reagent, now for example, if you take something like this, I will talk about it later as well, CH3MgBr. Now students, magnesium is extremely electron positive. We say very less electronegative, right? So therefore these bond electrons are further attracted towards carbon. So carbon is partially negative, this is quite partially positive. So these bond electrons, it's not a very stable bond. The bond electrons are waiting to be given to carbon, right, or given to something else to form a better stable molecule. And we know that these when we first learned about greenhouse reagent, we said they are capable of accepting proton from even very least acidic substances. Even with water they will react and take a H plus for them, right? For example, the alkyl group will pull a hydrogen even from water, and the OH group will go with magnesium, right? So it will be OH MgBr, and this one will take hydrogen and it will become CH4, right? So why? Because these bond electrons here are very easily donated. These bond electrons are very easily donated. They are very easily donated by this CH3 group to someone else, right? So CH3 group in this section is acting as a nucleophile. They can easily donate these bond electrons to something else. Is that clear? So therefore, students, what you see is whenever you have an aldehyde or a ketone, right? I'll take a aldehyde again, but students, ketones are also the same. I will draw a ketone for you, right? Otherwise you will think ketones don't undergo anything. So we will take a ketone, right? So if you take this ketone and react it with CH3MgBr in dry ether, right? So we'll write, this is the overall reactant, CH3 MgBr dry ether, and then you have to do a second reaction as well, that is addition of water, H plus. I will explain this to you through the mechanism, right? H plus H2O, you produce something like this, CH3 OH, this oxygen becomes a OH group. This part will stay here as CH2 CH3, right? So this part is staying here, and this section, CH3 section that was connected to MgBr, will get connected here. Is that clear? Understood? So whenever you are writing the overall reaction, we have to write the greenhouse reagent. That's the first step, and then there's another step, that is addition of water. That is very important, crucial. If you don't write this one, you are getting a different product. Okay? So first take this down. So let me, as you take it down, I'll go down and bring some water. For me it's a bit difficult, so you quickly take that down. I'll be here in 2 minutes. Are we done? Right. Now let's take down the mechanism. Mechanism. So here, students, again, if you take this carbon oxygen double bond, CH2, CH3. Here we have a partial positive charge here and partial negative charge here. And we have CH3 Mg Br. So you can write here easily donated electron pair. Right, this is the easily donated electron pair. Acts as a nucleophile. Is that clear? It acts as a nucleophile. Complete this thing from here the way you think, but I'm just wondering whether it'll be we'll see how you do it. I'm a bit worried that you will write something completely different and you'll get it wrong. So this is what you should know. You will produce, we normally show these two steps together. Let me draw this. Now the new CH3 group is attached here, and at the same time we know this oxygen becomes negative, right? Right, so when this group donates a bond electron pair here, MgBr will be positive. They will quickly react and connect with the oxygen here. So what you will have is O MgBr here. Is that clear? OMgBr will be quickly formed. So this is the very first step. This is the very first step, right? Mechanism. First step. But after this, I will write the second step on top. If you add H plus H2O, that's the second step of the mechanism which you should know. H plus H2O. Then it will change to this. Directly we need to write this, no need to show electron transfers at this point. This is what you should write. Right, so basically these electrons are given to H plus and MgBr will go with a OH group. Right, so currently if they have asked how to produce the final product through a reaction that involves magnesium bromide or through a reaction that involves Grignard's reagent, keep in mind after the addition of Grignard's reagent, if you don't show the addition of water or H plus and water, which is the second step, if you don't show that in the reaction, your final product is this. If you show that we have added water, then the final product is alcohol. Is that clear? So sometimes they trick you. They don't give you this part. They ask you what is the final product. Final product is then this then. Exactly. If you just add magnesium bromide like Grignard's reagent and then don't add water, this is the product. If you add if you add Grignard's reagent and then plus add water, the final product is this. If you don't add water, the final product is this. Is that clear? So please read the question carefully. Take a look at what is written on the arrows then only you should be providing your answers. Is that clear? Sometimes students, that's another thing. At the exam, sometimes they give you this flow chart type of thing, right? So where you have fill the boxes and the circles, right? So we say this reactant is there, and then we have a product here, and then there's another product formed, and then only the final product, right? Sometimes in those boxes, they do this Grignard reagent addition in 2 steps, which is first one forming adding magnesium bromide Grignard's reagent and producing this product, and then this gets converted to this. Is that clear? So sometimes they break it down into 2. Sometimes they don't. Sometimes they have one box here, another box here, straight. You do both the reaction, addition of Grignard's reagent plus addition of water together is done sometimes. Sometimes they break it into 2 pieces and write. Is that clear? So you have to be mindful when doing questions. Do this one. AC is also not properly working, no? Right, take it down. Right. Already done? Some of you? Whew. How do you all stay in school? I'm just wondering. School, is it difficult these days? Huh? Pretty chill? Is it hot in school? Only you 2 go to school? Only these 2 go to school? None of you go to school? No? Now you go to school? In the sense, now you don't go to school anymore. Only you guys are going to school. Oh, okay, then no problem. I was just wondering what I can do. Right, brilliant. So that's good news. Right, we'll do something about it. Don't worry, I'll take care of you guys, so don't worry. Right, are we done with this? Okay, so now students, these kind of reactions are quite important for a reason. So I'll tell you what the reason is. This type of reaction actually allows us to extend the carbon chain's length of molecules, right? So imagine sometimes we want like a short carbon chain molecule to end up being a large carbon chain molecule, right? Imagine carbon chain contains only 2 carbon atoms. We want to have a final product that contains about 4 or sometimes about 6. Then we can do those kind of reactions through this. Is that clear? We'll do some questions so that you will have an understanding about this, right? So take some questions down. We'll start simply and then we'll gradually move to better difficult questions. Quickly take a small question down. Did you take these mechanisms down? You understood? Right. Students, we'll move fast because I will not give you too much time to do these questions. So we'll start something like this. This one is easy. I have to give you more. Quickly do this too, and then I'll quickly get to the other parts. Hurry up, please. Is there anyone who's done? First one is easy. Second one is also super easy. Off. Are you done? Okay, let's see. Right. I'm sorry students, here I have written a wrong formula. Is it CH2 here? Should be CH, no? Should be CH. It can't be CH2. Right, so now that's correct now. Can we quickly do this? The first one is easy. What do? We need to add a what is the additional part that is added here, students? This section, right? CH2, CH3. So you add a greenhouse reagent there, right? We can directly add that greenhouse reagent. I didn't say anything about using this as the only organic reactant. CH2, MgBr, dry ether. Second one is H plus H2O. We get this. Is that clear? So what happens is this CH3 CH2 part connects to this carbon like it has there, and when you add H plus H2O, this O turns into OH, right? Like we have written there. Is that clear? Do you see this now? Right? And then let's take a look at this one. Now this one seems to be like something bit more complicated. But if you take a look at this, you can see we have CH3 carbon with oxygen and then CH3 again here. Here we have, apart from CH3 groups, we have another different group here as well, but it's not very apparent, it's not very clear, right? So what has happened here, students, actually a greenhouse reagent. We have now increased the carbon chain's length. Carbon chain's length can be increased only in a few ways. We can use an alkyl halide. Can you remember alkyl halide and the addition of acetylide or nitrile group, or addition of alkoxide ion. You need to remember these. Then they will increase the size of the molecule. But apart from that, we also can use we can also use greenhouse reagent. Greenhouse reagent also increases the carbon chain's length by adding different other alkyl groups to the carbon chain. So now, if you take a look at this, if you attach another carbon section here, now currently it is only 3 carbon atoms long. There it is 5 carbon atoms long. Now what happens if you add, let's say something like CH3, you need to be able to see this. You will see this as we move along, right? If you added, now before I go into that part, let me ask you this. There's a double bond here. Let me ask you that one first. How can you form a double bond usually? What are the methods that you know to form a double bond? You can have a elimination reaction of an alkyl halide, right? Or elimination reaction with the alcohol, right? So alcohol is aluminium oxide and heat. So what if there was an alcohol here? So you can have a alcohol, something that looks like this. You should have a bit of knowledge to figure out where the OH would have been, right? If the oxygen would have, OH group was here there is 3 hydrogens, there were two hydrogens, yes, it could form a double bond here. Or if the oxygen was here, still it won't form a double bond here, it will form a double bond here. Now by looking at the structure of this, you can determine mainly the second carbon would have had a OH. You can just assume that was the case. Is that clear? And then this section would be here CH2 CH3, CH2 CH3. Is it understood? So now how can we get to this molecule? It's super easy, no? You can directly react this with CH3 CH2 MgBr, which is our greenhouse reagent in dry ether, and as a second step we can add H plus H2O. Then what happens? You get to that alcohol, right? Sorry, in this case I have drawn the arrow pointing downwards. Now we first make this, and then this will be converted into a double bond by adding concentrated sulfuric and heating, or we can add what? Anhydrous aluminium oxide and heat, right? We can write anhydrous aluminium oxide and heat. So rather than removing a hydrogen from here, this will be removing hydrogen from the carbon where the hydrogen number is less. So the double bond will be present between these two carbons. Is that clear? So that is how you would get to the answer. So take that down. You should be able to see this next time I give you a question. Okay? I'll do one more question after this. Shall we do another question now? Can I erase this? Now we are in the, I'll give you a small hint, so because now you all are quite aware about the fact that we are talking about greenhouse region, right? So my conversions will have a greenhouse region somewhere, right? So obviously that's something you should know. So now try to at least train your eyes to see these things. That's what I'm trying to do, trying to get you all to see that it has happened through a greenhouse ray. So your brain develops an idea, okay, this kind of reaction happened through a greenhouse ray. Right. What? Is that correct? This reaction can happen in another way also, which we will learn later. That's called self-condensation reaction, but for the time being, use what you know to do this. Are you done? Anyone who's done? Almost didn't see you there. Yes. Very good. Yes. You can even use PCC also, okay? Because it's a ketone anyway, alcohols will turn to aldehydes or a ketone using PCC. But if you use primary alcohols and those kind of oxidizing agent, it will go to carboxylic acid. Okay. But yeah, correct. You're correct. Can't remember what to use. What have you done here? No, can I know why you kept the double bond over here? You can't, right? It will be alcohol, OH. Exactly, correct. You can use PCC or other oxidizing agents as well. Correct. Students, PCC is not the only one. You can use H plus KMnO4, H plus K2Cr2O7, right? So first of all, do the, here we can see 2 carbons. So here this says 4, right? That means this section is additional, right? So you try to add this section through magnesium bromide, greenhouse reagent addition. So you can write CH3CH2 MgBr with this, right? All right, you have shown it in 2 steps. That's also correct, very correct, no problem. And then we are producing this. Okay, good. Is this all? No, don't do this, right? So I told you we are using, what do you call it, greenhouse reagent, right? So what do? We have this section. We can say something like that is here. We can't say this section is exactly the same as this. We have reformed it, okay? So do you see there's 2 carbons here, there's 4 carbons here. That means there are additional 2 carbons that came into the picture. So we can bring additional 2 carbons like this through a greenhouse reagent, right? So you bring that here. When you add greenhouse reagent like that here, you are adding CH2CH3 group here, and this will become a OH. Right, so now OH is here, CH2CH3 is connected here. So if you have alcohol like that, secondary alcohol, can't you oxidize it to form a carbonyl compound? You can. right? So this is all that you need to do, students. Pay attention. So you can see here there are 2 carbons, there are 4 carbons here. 2 carbons and 4 carbons. All that you have to do is what? You can realize 2 here, 4 there. I have to bring in another 2 carbons through Greenhouse reagent. I have to bring in another 2 carbons through Greenhouse reagent. I told you I'm going to use Greenhouse reagent. So this is what I'm going to use Greenhouse reagent for, to increase the carbon number. 2 carbons to 4 carbons. Since I want to increase the carbon number, I can use Greenhouse reagent. So I can use this. Now you can even, now I saw one of you have done this, that's also correct, that's fine. So imagine if you are someone who wants to do it this way, you can just show CH3, CH2, MgBr. This is another way of doing it, right? So then you show the product that is produced, CH3, CH, right, this hydrogen, and then this will be O, MgBr plus CH2, CH3. I'm talking about the mechanism here. Can you remember? We had this part here, and the oxygen with a double bond turns into OMgBr. Then this hydrogen is here. Now we normally do this greenhouse reagent and water together. No, in this process I'm doing it in 2 steps. This is also correct, no problem. You can write H plus H2O, H plus H2O. So then you produce a alcohol, CH3, COH, CH2, CH3, and then hydrogen. And then here this will convert everything into carboxylic acid, a ketone here. So this is a secondary alcohol with any oxidizing agent like H plus KMnO4, H plus Cr2O72 minus, H plus CrO3 or PCC. Any of those 4 can be used here. Right? Since PCC is the easiest for me to write, I write PCC, but anything can be written here. Any oxidizing agent would do this. Is that clear? So you should be able to do it. So this is, now I just thought I'll write it this way because I have been writing it always like this. No, for a change I wrote it this way, right? But you could have written something like this, like directly turning into the alcohol. Is it understood? Right. One more question. I'm not still happy with how you all do it. Still not happy. Still not happy. We'll do one more. Okay. So I'm only using things you have learned, students. So this is like, I tell you, you have to first climb step 1, step 2, step 3. Now you have passed few steps here. About 5-6 steps you have done. Now again, if I give you a question, you sometimes forget all the first few steps and try to only stick to the current step. You are jumping in place without looking at other things that you have done. So I want you to do that. Like I want you to go and revisit the things we have done before, because without that knowledge you can't be operating in this particular section of the lesson. It will be difficult for you. I can erase this, right? Brilliant. Write this question now, a bit of advanced question, right? Using the initial reactant as the only organic reactant, complete the following conversion. Bear with me a second, students. I'm still wondering whether this is possible. Bear with me a second. Because I haven't told you about aldol condensation yet. Just give me a second. No. Since I haven't told you about aldol condensation yet, this is not possible for you. So we'll be mindful. It is not as complicated as you think. Keep in mind, be mindful. It is not as complicated as you think. Avoid additional steps. I have a feeling you guys are going to have one additional step, right? If you want to add a Br there instead of a Cl, you can add PBr3. PBr3 is also working similar to PCl3. So PBr3 can be added to get to a halogen group there. Or even a PCl3, or is this fine? You can form a greenhouse region there as well, no problem. Is there anyone who's done? If you all don't get to this, I'm gonna have to kick most of you all out, because this is super easy, not at all difficult. Huh? What if I told you, you would feel like, oh my god, how I didn't see this. Now listen, none of you are anyone who's done? From the answers that I can't check, no, you are close to the answer, right? Nobody. So what has happened here? Obviously I'm going to ask you to use this is a greenhouse reagent question. Even if it is not given in the question, you should be able to figure out 2 carbons, 4 carbons. Most probably greenhouse. Most probably. Is that clear? Most probably greenhouse. So let's attempt to do this in a greenhouse reagent manner, like without using any other organic compound. So first of all, to react with greenhouse, we need an aldehyde or a ketone. How can we produce aldehyde or a ketone here? Quite simple. This is a primary alcohol. How do you convert primary alcohol to aldehyde? PCC. Right, we had PCC. So we have this. Now you have to have logical thing. Don't get too caught up in your mind, like thinking how is this connecting. No, ask yourself these questions. 2 carbons, 4 carbons. Okay, how can we connect these two? I know about alkyl halides, but it doesn't seem to be working here. And then I know about greenhouse. Right? Our greenhouse reagent also increases. So we'll try that out. So to react with this, we need a greenhouse reagent. And in the question they say you can't use anything else other than this one. So now we have to make greenhouse reagent starting from this. Fine, can do. Let's add PBr3, right? No problem. So we get a CH3, CH2, Br, okay. And then what? We can react it with magnesium in dry ether. Magnesium in dry ether. You produce what? CH3, CH2, MgBr. Right? Obviously in dry ether. Right? So then what? You add them together. So let's say we add these two together. Again in dry ether medium, okay? Dry ether medium. That's the first one. Second one, H plus H2. Second one, H plus H2. So it turns into CH3, CHOH, CH2, CH3. Now I was talking to you about don't increase your steps too much, because some of you will see OH is here, but the Cl is here in this corner. Let me close this and form a double bond and put peroxide in front of HBr or something and get it here. Right? Do you understand? Some of you do that, but you need to see this OH functional group is present on the second carbon. Here also, if you are counting carbon atoms, Cl is present on what? Second carbon, right? This is not the second carbon at this point, right? This is the second carbon. So we can convert the OH directly into a Cl group. How do you do that? PCl5 or PCl3. Is that clear? Isn't that simple? Since we were in greenhouse, right? Wasn't it? I told you that this is greenhouse. It's like a very key hint. You should be able to figure this out. Like a huge help us done here. Copy this down, study this one, like you memorize this, do it on your own again at home. Okay? Anyone who got something similar to this, at least the first few steps correct? Anyone? I couldn't check your book, Praveen. Did you do the first few steps correct? All right. Now your eyes must be like, fixed on functional groups. Like for example, when you see a functional group, you should be like, this can turn into these things. Like, in cartoons and all that, they say these things and they say, like, get a map of everything that can happen. Just like that. You should be able to see this and figure out, okay, what else can happen through this. Do you understand? So you will come to that in your mind. I'm not saying like a cartoon, but you will come to that when you see this, you will have an understanding, okay, these things can be done with this functional group, right? And whether it will produce even more functional groups after the reaction. For example, students, if you went with an alkyl halide related reaction, if this is alkyl halide, another group comes and attaches here, it might lengthen the carbon chain. But then after the lengthening, no other functional group is there, right? Imagine I had an acetylide group here. So if alkyl halide reacts to the acetylide, you produce large carbon chain, that's it. No functional group is there. Carbon, there will be a triple bond, but no other functional groups will be seen, right? So whether you can figure out from there whether you can work your way towards where you want to be here. Is that clear? So you need to be able to figure those kind of things out. Okay, now enough. Yes? So normally the reason why I show dry ether here is this is we produced greenhouse reagent. It is in dry ether, but since I want to show two steps, do you understand? So I want to show that this and this is added together in dry ether medium first. That's the first thing we do. Normally when it comes to greenhouse reagent, we write no greenhouse reagent in dry ether. Do you understand? We have produced a greenhouse reagent. Greenhouse reagent is added with dry ether. That's the first step. And then second step only H plus H2O. Is that clear? Okay. Now let's move on to the next part. Take a new heading. Self-condensation. Self-condensation reactions. Under that, please write under that you can write carbonyl group has a strong electron withdrawing nature. A strong electron withdrawing nature. Due to this, carbon atoms attached to carbonyl carbon atoms attached to carbonyl carbon becomes electron deficient carbon atoms attached to carbonyl carbon becomes electron deficient, and the hydrogens in those carbon atoms becomes acidic. Hydrogens in those carbon become acidic. Let me explain this to you here. So when you're talking about this carbon-oxygen double bond, this particular carbonyl carbon is usually referred to as a strong electron withdrawing group, functional group that is strongly electron withdrawing, pulls electrons away from other groups. Now these carbon atoms that are directly bonded to it are usually referred to as alpha carbon. Starting from here we call it alpha carbon, and then if you have another carbon it will call it beta carbon, so on and so forth. So alpha carbons are the ones that are directly bonded to this carbon atom, right? So those carbons become quite partially positive charged because this carbon is pulling electrons away from the alpha carbons. Is that clear? Now because of that, electron density around the carbon atom here decreases. Now when that happens, these carbon hydrogen bonds get quite polarized, and it's easier for these carbon hydrogen bonds to break and release hydrogen as H plus ions. Is that clear? So it's not like a strong acid, but these alpha carbon rated hydrogens, also referred to as alpha hydrogens, are somewhat acidic, tiny bit. Is it understood? Tiny bit acidic. So this is the reason behind what is known as a self-condensation. In basic medium, especially in strong base such as sodium hydroxide medium, due to this reaction you can form a nucleophile here, and that nucleophile can go and attack the carbon here, because we know nucleophiles can attack the carbonyl carbon. We saw the very first reaction, cyanide groups attacking the carbonyl carbon and attaching there, right? Can you remember? So something like that can happen here as well. Is that understood? Right. So under that, please take these examples. Don't write the release of these. You can write these hydrocarbons, alpha carbons are becoming acidic acidic hydrogens. First of all, please take this down. First take this down. Is that clear? You can write under that. Hydrogens bonded to alpha carbon are referred to as alpha hydrogen. Hydrogens bonded to alpha carbon are referred to as alpha hydrogen. And they are acidic in nature. Okay, right? In the presence of a strong base, a carbon ion can be formed. In the presence of a strong base, a carbon ion, not carbocation, it's carbon ion, negatively charged ion. A carbon ion can be formed. and the carbon ion becomes stabilized through resonance. Carbon ion becomes stabilized through resonance. So we'll do one example there under this, right? This is our alpha carbon, and then imagine you have a strong base added here, right? Strong base added here. So obviously carbon hydrogen bond, now this carbon is also partially positive because the electron withdrawing effect, but carbon hydrogen bond is polarized in such a way hydrogen becomes partially positive, right? Always hydrogen is 2.1 electronegativity, carbon is 2.5 electronegativity. So therefore this bond is polarized in such a way hydrogen is electropositive, or hydrogen is getting partial positive charge. So now this will go here and these electrons will go here, and you produce your carbon ion. You produce this carbon ion. If you have a question, you can ask, let me know. Any question? Yeah? Doubt? No? Sure? Right. So you produce a carbon ion. Where is the negative charge here? Obviously this carbon has a lone pair now, the carbon is negatively charged. So the carbon ion that is produced, right? The carbon ion that is produced is stabilized through resonance. It is stabilized through resonance. Now what do I mean by that? Now this double bond this lone pair can come here as a double bond, and carbon oxygen bond can break and its electrons can go here. So now instead of carbon bearing a negative charge, now a very electronegative element is bearing a negative charge, which is actually a bit more stable. So therefore through resonance we can have a bit of a higher stability now. Unlike carbocation, this one is slightly more stable, right? Because the resonance plays a role and help the molecule out, or the ion out, to become a bit more stable, right? So imagine if having a negative charge on carbon is not very stable, now through resonance it is going to be on oxygen. Oxygen is anyway a very electronegative element. Having a negative charge on oxygen is quite okay, right? And this keeps on happening, resonance, right? So yeah, under the topic that I gave you, or just sentence that I gave you, take this down as well as this and label this. Students, what day is easier for you to be here? Tuesday morning or Monday morning? Monday morning at a stretch will be difficult. I'm just wondering. Staying here from 9 to 4, will it be difficult? No? No? No, it's okay? Fine. If you are saying it's okay, it's okay. Are we done now? Right, as a new sentence please write. The produced carbon ion can act as a nucleophile, and can undergo a nucleophilic addition reaction with the carbonyl compounds present in the medium. Can undergo nucleophilic addition reaction with the carbonyl compounds present in the medium. Is that clear? Right. So let's understand what that means. So students, now imagine in the medium still there are other, imagine if you take, this is ethanaldehyde, right? If you add ethanaldehyde, the very first thing that happens is, yes, certain amount of ethanaldehyde can turn into a carbon ion, and then there will be other ethanaldehyde that has not undergone anything, it's still there like so. And we know here the carbon oxygen bond is quite polarized, carbon is positive, this is negative. And now we have a carbon ion. So carbon ion is something like this, CH2, C double bond O, H. The negative charge here is on the carbon atom here. And I showed you carbon atom has a lone pair as well, which is acting as a nucleophile. So now this can undergo a reaction. This can attack, sorry, bear with me. I want to show the electron transfers in a different color. CH3, COH. I'm going to write this hydrogen here, okay? I'm going to bend this hydrogen and write it here. And I'm going to attach this here. CH2, C double bond O, H. Actually students, I directly wrote the hydrogen there, but normally O minus is there, and O minus will take a hydrogen from H plus that is out there, or it can take hydrogen from water, right? So either way it eventually produces this. I will show that as well, otherwise some of you might be wondering what will happen, right? So I'll just show it like this. Is it understood now? Right? So now that is called self-condensation. Same molecule added together through what? A carbon ion that was formed. Why was the carbon ion formed? Because alpha hydrogen is acidic. In the presence of a strong base, alpha hydrogen will leave, forming a carbon ion. Carbon ion is somewhat stable, so it will stay in the medium, and carbon ion will react with the partially positive carbonyl carbon and get added there through a nucleophilic addition reaction, and we eventually will form a molecule like that, right? So take that down. Under that, I have already given you the detail there. Take this down. I would prefer that you take down, I forgot this is a, what do you call it, alkaline medium. You will not have H pluses. So therefore, this is what is happening. Water will be there, it will take hydrogen from water. No H pluses are there in a strong alkaline medium. So therefore, water will give hydrogen and the water molecule will become OH minus ion. So there's something special about these. That is the next step. Can I write? Have you finished taking this down? Something a bit special about this. We'll talk about that and we'll finish it off. Right. Write down. The above addition product that is formed can easily be dehydrated. Meaning, students, we can remove water molecule easily here. Can easily be dehydrated, forming a double bond. When heated with acid. When heated with an acid. So students, dehydration of this is super easy. This can easily undergo dehydration reactions. So we have something like this, CH3, we have OH, here also we have hydrogen, right? CH2, C double bond O, H. So if you add H plus into the medium and heat it, that's it, H plus and heat. No need to talk about anhydrous aluminium oxide, concentrated sulfate. Don't have to say anything. If you just say H plus and heat here, then quickly this OH will leave with a hydrogen from the adjacent carbon. So OH should leave with the hydrogen with the nearby carbon. So normally hydrogen leaves from which carbon? Carbon with the lower number of hydrogens here. So the double bond will be formed here. So you will be forming something like this. Right, take that down. Done? Done? Some of you have already taken it down. Write down a question after this. Write the final product write the final product. Write the final product that can be formed when the following carbonyl compounds are added with sodium hydroxide. The following carbonyl compounds are added with sodium hydroxide. First one, CH3, So I just don't want you to write the mechanism or anything. Just write when you add it with sodium hydroxide aqueous. I want you to tell me what the final product would be. So you need to be able to figure out the final product without having to think about it too much. Meaning you have to come to a place where you see what the final product would be. And this is added with, again, sodium hydroxide. Can you please complete this task? Are we done? First one is easy. Shall we do it and see? So let me quickly do this first one. And if you haven't gotten to answers correctly for the first one, I will be checking your second one's answers. Let's see. First one is quite simple. This is alpha hydrogen, this is also alpha hydrogen. Either one can react, so there's no preference here. So either one can react. So we can say this one turns into a carbon ion by losing a hydrogen, and then this is the one that is getting attacked. So it's easy, students. Identify the way that you should write it. I advise you to do it this way. Write this section first. We have carbon here, CH3, and then we have a carbonyl carbon. We know carbonyl carbon will become OH, no? So we write that, right? Carbonyl carbon will become OH. And then CH3 part, I normally like to write this part bent down like so, right? So it's out of the way. I'm trying to connect the carbon ion here, but I don't always do that. It's up to you. You can do it the way you like. So now this is the one that is referred to as alpha carbon. This is also alpha carbon. We'll take this one as alpha carbon. Both are same. So if one hydrogen is lost here, this becomes what? CH2 minus. So that is what is getting attached here, because this is the one that is attacking another molecule that looks like this. So this gets attached to the already written group here. So then I start writing CH2 because alpha hydrogen leaves. So this is CH2, and then we have carbon oxygen double bond, yes, and CH3. Is that clear? So that is a product. Understood? Okay. So that's the product. We call this self-condensation. Back in the day it was quite known as aldol condensation, but now it's mainly referred to as self-condensation. Now let's work the second one together, right? Let's work the second one together. So we have this. Now this is aldehyde, so there's only one alpha carbon. This is alpha carbon, right? So we'll keep that in mind, right? So before we move on to any of that, we know that the alpha carbon, when it turns into a carbon ion, it is attacking this, no? So we'll just forget about alpha carbon for the time being. We'll write this section first. So we write, okay, CH3, CH2, CH2. Then we have the carbonyl carbon. We know very well carbonyl carbon will become a OH group. And this hydrogen, I'm going to write it here. Okay. Now I'm all ready, right? I'm all ready now. Now think about the carbon ion that is produced here. So carbon ion is produced when the alpha hydrogen that is present here goes away. So the negatively charged ion or the negatively charged carbon is this one. Alpha carbon turns negative, right? So the negatively charged carbon is the one that is connecting to the carbonyl carbon here. Am I correct? Yes. So what should be connecting here is our alpha carbon, right? This is what should be connecting to this carbon. So let me do that. This carbon, I will connect it here. See, the one of the hydrogens is lost, so I have to write CH, and then we have C double bond O, and then I have hydrogen. The other group that was connected to the alpha carbon, I can write it like this: CH2, CH3. Is it understood? Do you understand now? Right? So it's the alpha carbon that bonds to the carbonyl carbon. Clear? Alpha carbon is this one, the one that is directly bonded to the carbonyl. So this alpha carbon should be connected to the carbonyl carbon of another molecule. Right? Simple. So this is the final product that you get. Is it understood now? Let's see whether you understood that. Right? Do this one. Please do this one. Complete it. Huh? Very good, correct. Correct, yes. You wanted some recording by any chance? What is the recording you wanted? Week before last week, can you tell me the date if you don't mind? Is it the 10th?
Yes.
Today is the 24th, yeah? Your number ends with what?
33.
Right, I just sent it to you. Right, did you all get that? Can I see? Correct. What about you? Right, bear with me. So now, here, this one is the alpha carbon. Alpha carbon will lose a hydrogen. Then what happens? This will become negative, right? So this is acting as a nucleophile, this entire thing. So the nucleophile, you take another molecule of this, and the nucleophile attacks the carbon of the next molecule. So this is the nucleophile, this is where the lone pair is. So therefore, this carbon of another molecule will connect these two together. I will explain that to you in the board as well. So then you get the product that I'm talking to you about here. So students, I will explain this to you once more with the mechanism. So I asked you answer for this question, right? I will do the mechanism on top and I will write the final answer at the bottom. So here, in this molecule, if you take this molecule, I'll write the alpha carbons, hydrogens displayed. So this is our basic carbon and this is our alpha carbon, carbon alpha. These hydrogens are alpha hydrogens. So in the presence of a base, when you add sodium hydroxide, one hydrogen from this alpha carbon usually can leave, right? In certain molecules it can leave. So when it leaves a lone pair on the carbon atom, right? Imagine, it is the bottom hydrogen, or it is the top one, right? So I can write the lone pair on top. Now the lone pair is here. Imagine another molecule like this. Let's say I write it here, it will be easier. Imagine the alpha carbon was lost in this particular molecule. The alpha hydrogen was lost in this molecule. Now this is negatively charged as well. So this alpha carbon, so not alpha carbon, the carbonyl carbon is usually always partially positive. In any carbon compound, carbonyl carbon is always partially positive. It's electron deficient. So this carbon and the alpha carbon can form a bond because the alpha carbon has a lone pair. It can donate the lone pair here and start forming a bond with the carbonyl carbon. Is that clear? So when that happens, you produce something like this. We have this section without any change. You can see there's nothing happening here, CH2. But this carbon is now attacked by a nucleophile. I will show the nucleophile here directly so that some of you understand what's going on in that way. So basically this has happened. Do you understand? That has happened. But we don't like to write molecules like that sometimes. Even writing like that is fine, okay? No problem. Now we know this O minus will react with a water molecule and gain a hydrogen there. So I will write the final product. Final product is this. So how can we write the final product without having to write the mechanism? You have to understand it's the alpha carbon that bonds to the carbonyl carbon of another molecule. Alpha carbon of one molecule connects to a carbonyl carbon of another molecule. So if you understand that, it will be easier for you to get to the product. So we have to write this molecule here all the way up to the carbonyl carbon. I will write without making any changes. So that's the first thing I do, right? But once I get to the carbonyl carbon, I write the oxygen as a OH group. I write the oxygen as a OH group, and whatever the group that is present to the right hand side, I normally prefer to write it down like this. It's a preference, because in organic chemistry, writing a molecule is not like writing a molecule like this is not wrong, right? But somewhat not very clear, right? Sometimes when you're trying to find the like the longest carbon chain, it might be a bit difficult because it's bent. So when it's bent, you might take some effort. It might take some effort to find the longest carbon chain. But it's neater when you do it the way I say. So now we have come to this point, and this hydrogen is written down here, and then again take a look at the same molecule and figure out which one is the hydrogen alpha carbon. Alpha carbon is this one. So I need to connect this alpha carbon here. So now alpha carbon has mainly one hydrogen remaining. After one hydrogen leaves here, one hydrogen remaining. We have this group here in the alpha carbon and this group here in the alpha carbon. This alpha carbon directly connects to the carbonyl carbon of the previous molecule, and then it has an aldehyde section. It has a hydrogen, right? It has hydrogen. We normally write the hydrogen like this, CH, and apart from that, it has a whole alkyl group. So that alkyl group looks like this: CH, CH3, CH3. Is that clear? So we can write it like this. Basically, I have written the same section, but I have bent it like this and brought it up. Okay? So you should be able to figure that out. So now, with that, I will give you a small break, but be prepared for some questions revolving around this. I want to give you some good questions that come through this part. Okay? So be prepared. We will do some good questions that are asked or that are revolving around self-condensation of aldehydes and ketones. Okay? Right, take a small break and come. Now it's 5 o'clock. How long of a break do you need? 20 minutes, fine? Right. So be here by 20 to 25 minutes, will you? We'll start after that. 61. Right. We'll start with the question, students. We'll start with the question. Bear with me just a second. There are a few other reactions that I would rather do before doing this question, but we'll do a normal aldol condensation related only question, otherwise you will get confused later down the line. Most of the questions that I want to give you, I can still not give you because of the fact that we haven't done the rest of the equations, but we will start with a simple question like this. We'll start with a simple question like this. Simple one. Attempt it, please. Done? Right, I want to move on to the other parts as well, students. So this one is quite simple. Let's see whether you saw this coming. So I was talking about aldol condensation or self-condensation here. So we have sodium hydroxide, NaOH aqueous added here. So when you do that, it undergoes, as we know, a self-condensation reaction. Right, oxygen is becoming OH, hydrogen is written down, and the alpha carbon is connected here, and the alpha carbon has a CH3 group that will be connected here, and alpha carbon has hydrogen, and the other one is the aldehyde section. So this is what we have, right? So, but the thing is, this one has OH here, that particular product has OH somewhere else. Big problem, right? So what do we do here? What can we do? We can add a small amount of H plus and heat, acid and heat. When you add acid and heat, what happens? Easily double bond will come here. Easily a double bond will appear here. Bear with me a second, students. 1, 2, 3. Between 3 and 4 carbon only the double bond will appear. One, two, three, CH. This carbon now has a double bond, right? And then C double bond OH, right? So this is what we have. Now how can we get a what do you call it? How can we get a OH group attached to the other side? We can easily do that, right? Is that something difficult to do? Do we have to add peroxide and do all that nonsense here? Or is there something easier that we can do? Now you understood up to this point, no problem. And we learned when you learn in the theory parts about aldol condensation, if you have a little bit of acid and heat, what happens? Easily undergoes dehydration. So you need to remove hydrogen. Hydrogen can easily be removed from here because this has less amount of hydrogen. This has more amount of hydrogen. So the carbon-carbon double bond appears here, right? So that's what I have done here, right? So now after that you have to ask yourself, how can I get a OH here? What can we do? It's a single step. How can we do the addition of OH? What has to be done? Dilute H2SO4. Did we have to write HBr and all that nonsense? No. Why? Here when you add dilute H2SO4, we are adding a water molecule. Water molecule also has a group, we'll say a hydrogen group and a OH group. Hydrogen goes to the place where there is more hydrogen. Out of these two carbon, where is more hydrogen? Here. Oxygen goes to the place where there is less hydrogen, which is this case. In this case, it's carbon. So if you add dilute H2SO4 and slightly heat, you will have that produced. Is that understood? You can't forget the basics. Can't forget the basics. Okay? We are used to always adding HBr and switching things up. I wanted you all to be familiar with it because that is a very important reaction. But while remembering important things, don't forget the simple things. Right? That's something that you should keep as a motto in life also, right? Focus on the important things. Simple things are also important. Simple things are also important. Is that clear? Right. So after this, take a new heading. We'll finish off aldehydes and ketones today, and we'll move on. So aldehydes and ketones are super simple students. Once this is done, we'll be moving on to carboxylic acids, and then the last lesson is again a very simple lesson that can be covered easily. So take a new heading, reduction of aldehydes and ketones. Reduction of aldehydes and ketones. Under that, take a new subheading, reduction of aldehydes and ketones to alcohols. Reduction of aldehydes and ketones to alcohols. Right? Mainly the following two reducing agents are used. Mainly the following two reducing agents are used. First one, lithium aluminium hydride in ether. Right? You can write under this strong reducing agent. Strong reducing agent. And then after that, under that you can write, it is too reactive to be used. It is too reactive to be used in methanol. Or it is too reactive to be used in methanol, or it is too reactive to be used in methanol or water. Therefore only ether medium is used. Therefore only ether medium is used. As a new point, after reaction with lithium aluminium hydride in ether, after reaction with lithium aluminium hydride in water, in ether, water must be added in a second step. Water must be added in a second step to obtain the final product. Example. We normally write H plus H2. So you write this as the final product. Is it understood? So you can always see what happens is this carbon oxygen double bond turns into OH, right? Rest of it becomes hydrogens. Is that clear? So when you have CH3, CH, in this case we have oxygen becomes a OH group, and there's another hydrogen that can be attached here, so we form CH3, CH2, OH. Here we have CH3, CH, the same. This carbon gets another hydrogen, and this oxygen becomes a OH group. Is that clear? So it's again an alcohol. Now if you are paying close attention, I will give you this point anyway later on. If you reduce a aldehyde, we only produce primary alcohols. Whenever you reduce a ketone, you produce secondary alcohol. Now we know primary alcohols, when reacted with a PCC, we produce aldehydes. Ketones when oxidized, secondary alcohols when oxidized, we form ketones. You know that this bit, right? Tertiary alcohols when oxidized, does anything happen? Nothing happens. Can you remember this? Right? So you need to keep those things in mind. So this is how it's done, right? So let's move on to the next part quickly. Write down the second oxidizing agent. Sodium borohydride. Sodium borohydride is the second one. Sodium borohydride, usually used with methanol. You can write not as strong as lithium aluminum hydride as a reducing agent. Not as strong as lithium aluminum hydride as a reducing agent. So lithium aluminum hydride is a stronger reducing agent. Right? So the second point, right? Second point you can write. This does not require a second step where water is added. This does not require a second step where water is added to obtain the final product. Example: sodium borohydride plus methanol produces that. Same thing. Can you write this down? So this is not a very strong one. You will realize why I mentioned that this is not very strong. You will see when it comes to carboxylic acid the reason. So for the time being, take it down. But remember, these are the reducing agents you usually come across in our syllabus. These days it's still sunny and warm. Okay, so then finally, as a separate 2 points, please write. When aldehydes, this is very important, put a star point. When aldehydes are reduced, primary alcohols are formed. When ketones are reduced, secondary alcohols are formed. No need to take anything down. Just in the previous ones, you can write this is an aldehyde. and this is a primary alcohol. No need to take another one down, you can just write this down. This is a ketone, ends up producing a secondary alcohol. Primary and secondary alcohols are produced. You can write a main new heading after this, main new heading. Clemmensen reduction. Clemmensen reduction. Right, Clemmensen reduction. Reduction. Don't mix up the S's and O's and E's. I actually mixed the two up here. So Clemmensen reduction. That's a new type of reduction. Apart from the two main reducing agents we discussed, there's another one, Clemmensen reduction. Again, right? Clemmensen reduction is carried out. Clemmensen reduction is carried out when aldehyde or a ketone, is reacted with zinc in mercury, and concentrated HCl. This reduction converts aldehydes and ketones to their corresponding alkanes. So we have zinc in mercury, Hg, and conc HCl. So in this case, this is very important because unlike the other ones, we don't produce alcohols. This entire carbonyl group just completely gets reduced to CH2, right? Or it gets reduced completely. So here we produce CH3, CH2, CH3. The corresponding alkane will be produced. Is that clear? Very strong reduction this is, okay? So something to keep in mind. So now, normally students, most of the reductions, especially lithium aluminum hydride and sodium borohydride, we say they produce hydride ions. Now not H plus ions, hydride ions, H minus ions. So those H minus ions are going to, we say, not in this case, in the previous cases, they are going to act as a nucleophile and attack here, and then this will become OH group and the hydrogen will be attached here, right? So most of the reducing reactions are referred to be nucleophilic addition reactions. Right, that's also, now we are done with the reducing parts, done. But as an important key point, right, just write a small subheading, important detail or important. Okay, right? The reduction reactions carried out through common reducing agents, reduction reactions carried out through common reducing agents such as lithium aluminum hydride LiAlH4 and sodium borohydride NaBH4 takes place through the hydride ions they form. The hydride ions they form. Therefore, those reduction reactions are considered to be what? Considered to be what? Nucleophilic addition reactions. So these are MCQs, okay? These are MCQs. It is considered to be what? Nucleophilic addition reactions. I will ask these questions also later down the line. Okay, everyone. So now we are moving on to the final session or final part of our final part of our aldehyde and ketone theory. That is the oxidation reactions. Now, funny thing about this is, we know any aldehyde, any ketone can undergo reduction. But when it comes to oxidation, can both of those undergo oxidation? Can aldehyde undergo oxidation? Can aldehyde undergo oxidation? Can aldehyde undergo oxidation? My goodness, I have repeated like in 3 different tones. Still no answer. Aldehydes undergo oxidation, who says that? Okay, everyone is under the impression aldehyde doesn't undergo oxidation. Okay, ketones undergo oxidation. Both don't undergo oxidation. Did we not do alcohols before coming here? You all did alcohols, you did the alcohol lesson before coming here, right? So what did we learn about primary alcohols? Primary alcohols when oxidized forms first what? Primary alcohols when oxidized forms aldehydes first, and aldehydes further get oxidized to form aldehydes further gets oxidized to form carboxylic acids. Secondary alcohols when oxidized form ketones. Ketones do not further oxidize. Ketones stay there, right? That's it. Tertiary alcohols do not undergo oxidation at all. And we learned about these things. You can't forget. I think last week, right? Last week is where we did alcohols. So you can't forget these, right? I need to do more questions from alcohols. Let's see how you guys do. I'll give you a question after this. We will have time after. I need to first cover the theory parts, and I'll give you some questions to see if you remember this. Alcohols also, right? Alcohols, alkyl halides, we can nicely combine them together. Right, let's see. Now, after these, one thing to understand is when it comes to oxidation reactions of aldehydes and ketones, aldehydes are the only things that are undergoing oxidation. Ketones do not undergo oxidation. So this is a really good way to separately identify aldehydes from ketones. Is that clear? Imagine you do a chemical reaction you were trying to produce either aldehyde or a ketone. Let's say you don't know which one got formed. You have no idea whether it's aldehyde or whether it's a ketone. So how can you separately identify aldehydes and ketones? You can do oxidation reactions. Now for example, if you use, I will tell you the basic ones. If you use H plus KMnO4 to oxidize aldehyde, what happens? Aldehyde get oxidized to form carboxylic acid. What happens to H plus KMnO4? What is the color change? H plus KMnO4 or KMnO4 permanganate ions are purple. You can see a purple to clear color change. If you use potassium dichromate, dichromate is orange. When dichromate is oxidizing the aldehyde, dichromate turns into chromium 3 plus aqueous ions. What is the color change? Orange to green. What else? Another good one. Now some of you are doing biology, right? Students who are doing biology, only a few students I remember. Brilliant. Only the girls here does biology. So now tell me, when it comes to biology, we talk about Benedict's reagent, right? Fehling's reagent. You are using Fehling's and Benedict's to identify what? Reducing sugars. What is the main cation in the Benedict solutions and the Fehling solution? The same cation is there. What is the same cation that is there? Copper. What is the color of those? They are slightly more towards blue, right? So copper 2 plus ions are there, right? A tartrate of copper 2 plus is there. So copper 2 plus ion, students, can oxidize when given the right conditions, it can oxidize the aldehyde. Aldehyde turns into an ion of carboxylic acid, right? Because the basic medium is used, so therefore carboxylic acid reacts to form carboxylic acid and ion. Anyway, either way, I'll explain this to you in detail. So copper 2 plus is turning into copper 1 plus, right? So there is also a color change. Copper 2 plus is blue in color, it's a solution. Copper 1 plus reacts with the oxygen that is there and form copper 1 oxide, which is a brick red color precipitate. Again, another way that we see a very prominent color change. Right, so those kind of all of the oxidation reactions, there's another very good one called Tollens reagent, I'll talk about it later. So all of these oxidation reactions of aldehydes produce very prominent color changes, very prominent observations, which we can use to separately identify aldehydes from ketones. Is that clear? So take a new heading. Oxidation reactions of aldehydes. Within brackets, write identification tests of aldehydes. Within brackets, write identification tests of aldehydes. Identification tests of aldehydes. Right. So let me write them down. First of all, you have to write a small sentence. You can write, as learnt in earlier theory parts, ketones do not undergo any oxidation reactions. However, aldehydes can easily be oxidized. Aldehydes can easily be oxidized to its carboxylic acid with the use of different oxidizing agents. With the use of different oxidizing agents. So this is the observation. Under each reaction I will write the observation, right? So I am writing the product that is produced, right? The product that is produced is also quite important. So this is the product that is produced. Apart from that, the color change will be written here. So we have Cr2O7, which is the colored compound. So this is orange in color, and it turns into a Cr3 plus, which is going to be a green color solution. Green color solution, orange solution, green color solution. This is a purple solution, turns into color solution. So if there's a precipitate, I'll definitely let you know. Students, I will have to erase something to write the next one. So I believe you all will have space. Some of you have started taking it down at the end of a page, no? Right, it's okay, it's okay. You can take it down in the next page in that case. So the last one. Can I erase the top one or top two at least? Right? Top first one? Okay. Right. I'll wait for a second then. Right. So the next one is this. That's also a very nice observation. So we have something called, now you will be getting arrow pointing downwards, right? Like, because it's continuation. So that is Tollens reagent. Tollens reagent. Tollens reagent. Right, it is also known as ammoniacal silver nitrate. Ammoniacal silver nitrate. Basically, it's a silver ammonia complex. Silver ammonia complex. So I would have spoken about this under complexes that we have done. Right, silver ammonia complex, ammoniacal silver nitrate, or in other words, known as Tollens reagent. This is obviously basic because ammonia is there. This is in ammonium medium. So therefore, the produced product will not stay as the carboxylic acid. Instead, it will stay as the carboxylate anion because the medium is basic. Medium is basic. So the observation would be the silver 1 plus ions in the medium. Now it's a complex that is present here. It turns into silver solid. This is the basic reaction that is taking place. I will talk about this in detail later on. So when you do this, what we actually do is we mix the Tollens reagent and the aldehyde together and you put it in a water bath. Right? You put it in a water bath. So and then you heat it. So when you heat it, what happens is the reaction will take place, and due to the reaction, the produced silver actually gets coated in the inner walls of the tube. I believe I have shown you this video also, right? Have I? So due to the reaction, the inner walls of the tube get coated with the silver that is produced, right? So this inner wall now starts to appear like a mirror. Is that clear? So it has a nice mirror finish. You can actually see your face through it. Understood? Because basically you have a glass coated with mirror inside. So not mirror, coated with silver inside. So it becomes a mirror. So you can write, this is Ag coated. Ag coated on the inner walls of the test tube. Silver coated on the inner walls of the test tube, and we can see silver mirror is observed. Silver mirror, that's the observation. We say silver mirror is observed. Silver mirror is observed. Now this is a water bath. This is a water bath. right? So I will erase these unnecessary parts now, otherwise it will clutter everything. Is that clear now? Now you need to understand these are the main identification tests that are out there. You need to know every observation that you get. Is that clear? So when you use Benedict's reagent or failing solution, what happens? The medium of Benedict's and failings and tolerance are all basic. Those mediums are basic. So therefore, although the oxidation process happens, we don't get the carboxylic acid. Why don't we get the carboxylic acid? Because originally the carboxylic acid is formed, but it is in a basic medium. So carboxylic acid will turn into a carboxylate ion in the basic medium, right? Because they react. Is that clear? So what you see is the carboxylate ion. You don't see the carboxylic acid there. If you want to get the carboxylic acid, then what do you do? What do you do? If you want to get the carboxylic acid, you can take this product and then you acidify it. You add strong acid like HCl. So HCl will provide hydrogens to the carboxylate ion and will produce a carboxylic acid. Now this is the like your COO minus. No, if I add HCl, HCl produces H plus. H plus and COO minus comes together and form COOH. Is that clear? So the carboxylic acid will be produced. Is it understood? Right. So these are the main reactions. All the oxidation reactions are covered here, students. There's no need to go beyond this point and talk about each individual reaction separately, but you do need to know the observations. KMnO4 has purple to colorless observation. Dichromate has orange to green observation. Failings or Benedict's. Failings or Benedict's. It has copper 2 plus, right? Copper 2 plus complex actually. So what happens when we add copper 2 plus and aldehyde together? Aldehyde gets oxidized. Copper 2 plus turns into copper 1 plus. Along with the hydroxide ions in the medium, copper 1 plus eventually produces copper oxide. Right? Copper 1 plus eventually produces copper oxide. We call it copper 1 oxide. Copper 1 oxide is a brick red color precipitate. We learnt about these in inorganic chemistry as well. Copper 1 oxide is, what is the color? Brick red. Right? So when copper 2 plus turns into copper 1 oxide, it produces brick red color precipitate. Brick red color precipitate. Here also basically silver that is present as a complex here, ammoniacal silver nitrate. This is present as a complex, right? This is a complex ion that is there. In the medium, this along with the nitrate ions are there. So we call it ammoniacal silver nitrate. Nitrate ions are also present, but it doesn't matter in this case to the reaction. So silver 1 plus ions will receive electrons and oxidize this. So the thing that is undergoing oxidation removes electrons. Those electrons are received by what? Silver. So silver 1 plus, actually students, since I am writing the basic equation here, it's okay to write the electron here, right? Silver 1 plus plus electron turns into silver solid. So that's the basic observation. When the reaction is taking place, the produced silver solid actually gets coated inside the boiling tube. So actually it's a very nice reaction. The inner walls of the test tube is coated with silver ions, not silver ions, silver solid particles. So outside when you're looking at it, it looks like a mirror. Is that clear? Because the interior walls of the boiling tube or the test tube is going to be deposited with the silver solid that is produced. Silver solid that is produced, it nicely coats the inside. So therefore, the entire test tube becomes a mirror, right? You have mirror finish, so you can see yourself. Is that clear? So that is the observation. So the observation is silver mirror formation. Silver mirror formation. Understood? Right. So these are the main reactions to identify aldehydes from ketones. You can write down. The above oxidation reactions, are used to identify aldehydes from ketones. Is that clear? Right. Then write a new heading. Identification test for both aldehydes and ketones. Identification test for both aldehydes and ketones. Within brackets write Brady's reagent. Right. So students, here we have a reagent called Brady's reagent. Now there are so many names for it. It's the same thing, okay? Also referred to as 2,4 DNP. Also the longer version of the name is 2,4 dinitrophenyl hydrazine. Right, 2,4 dinitrophenyl hydrazine. And the structure of it looks like this. Right, NO2 here, NO2 here. Right, so we have 1, 2, 3, 4. So this is the hydrazine section. This is the benzene. Benzene is usually referred to as phenyl group when it comes to alkyl groups. So this is hydrazine. This is phenyl. This is nitro. So what is the name? Now this is starting with the main functional group here, which is hydrazine. So this is carbon number 1, carbon number 2, carbon number 3, carbon number 4. So you don't normally learn the base, like overall naming of these kind of things, but it is referred to as 2,4 dinitrophenyl hydrazine. Is that clear? So you just have to memorize this name. So let's take this notes down, right? Take it down, students. Please make sure that this is clear. Nitro, TRO, hydrazine, actually ZINE. Hydrazine, ZINE, not ENE. Right, so take this down. So it's called Brady's reagent, 2,4-DNP, this same thing, okay? So please highlight it and say different names. For the same compound. Different names for the same compound. Brady's reagent, 2,4-DNP, 2,4 2,4 dinitrophenyl hydrazine. And then the structure of the molecule. Can write. Still copying down. Bear with me just a second, students. Everyone is not done yet. Write down both aldehydes and ketones undergo reactions with 2,4-DNP to produce an orange color precipitate. Is that clear? Right. Can write. These produced precipitates are known to be derivatives of (2,4) dinitrophenyl. You have to write this. 2,4 dinitrophenyl hydrozones. Derivative of dinitrophenyl hydrozones. So basically, students, only thing that we change is you wrote earlier 2 and dinitrophenyl hydrazine. The I changes to O, right? The produced derivative is referred to as a hydrazone, right? We use a hydrazine, and after that it reacts and produces a hydrazone. So let me show you what kind of reactions take place. So you need to take this down. So, but wait, you can copy it after I explain it, right? So let me take this down first so that you have a better understanding of what's happening. So we have 2,4-DNP. So we have hydrogen, nitrogen, again hydrogen, right? There are 2 nitrogens, keep in mind. And then we have the benzene ring. And on the second position we have a nitro group, and on the fourth position we have a nitro group. Right. So now this section actually acts as a nucleophile and get added here, and then it's actually going through something called a addition elimination reaction. Right? Addition elimination reaction. You don't have to be too concerned about that, but that mechanism is given in the syllabus, but most of the time this is not questioned. If you want, you can go through that part as well. So what happens here is, now I'll write the main reaction for the first one. You can draw the second one, right? So when these two react, you will be producing this product, CH3 C double bonded nitrogen here, double bonded nitrogen here, bear with me just a second, students. Not double bonded nitrogen here, sorry. This is the product that is produced. Right, so take this down, and I want you to complete the next one. I want you to complete the next. I think, no students, I was correct the initial time, sorry, bear with me just a second. So the initial diagram was actually correct. These two have a right, this is correct. So now listen. The carbon oxygen double bond is gone and carbon nitrogen double bond comes. So that is what happens. Sorry about that. So this is the place where the double bond is, not between the two nitrogens. The carbon oxygen double bond that we have over here, carbon oxygen double bond is going to be removed. In place we have a nitrogen connected there. So this nitrogen connected there. So nitrogen has to give up these two hydrogens and is connected there. Same story will happen here. This oxygen will go off and the carbon oxygen double bond will go off, forming a double bond just like that one here. Can you please draw the same product? Are we done? Right, so with this we finish our this is also orange color, and it also has the same kind of name, derivative of 2,4 dinitrophenyl hydrazone. It is also orange in color. So now sometimes there are certain reactions where we need to identify whether the produced product is a aldehyde or a ketone. So sometimes it could be a ketone. Now ketone identification tests are not necessarily there that much. So therefore we use this to identify whether it's a ketone as well. So ketone as well as aldehydes produce the same observation. Orange color precipitate will be produced. Is that clear? Right. So this brings us to an end. So we actually from here stop the reactions related to aldehydes and ketones. Okay. So I thought we'll do a past paper question for the remainder of the time. What do you like? I have two questions. One is somewhat simple. Then there's another one that is not so simple. Both are nice. I would.
How come there are only two carbons there when we started with 4?
Oh, sorry. Yes, we need to be writing the rest of the section as well. So this is the one that is connecting. So please write CH3, CH2 here. You don't lose any carbons. Okay? You don't lose any carbons. Right, so which one do you like? There's a bit of a difficult question as well as a easy one. What do you like? Are you all getting worried when you don't get things wrong? So if that is the case, we can start with the easy one. But my heart is set on a bit of a difficult question. What do you like? Easy one? Okay, difficult one? Right? At least one student is there for the difficult one, so we'll do the difficult one. No? So can you please take down this question? Let's see whether you can get to this answer easily. All right? Do this one. CH3 C triple bonded carbon here, hydrogen here. I will help you in certain ways. It is turning into eventually this CH3 double bond carbon here, again CH3. Try to get this done. And the thing is, you are not supposed to use any other organic reactant other than the one that you already have here. Although I told that this is a difficult one, it is using mainly some reactions we have studied today. At least, like, one of the major parts of this is something we have studied today. What did we study today when it comes to lengthening the carbonyl chain? Now you can see the carbon chain is double, no? Sorry? We learned two doubling reaction, like carbon chain length increasing reaction. One is aldol. The other one is Grignard's reaction. So see which one can be used. One of the two is used here. I will even help you. Right? Grignard's. Okay? Use Grignard's here, please. Right? Now you should be able to do it. Students, in the question, they have given the chemical that you can use. Let me write the chemicals you can use. NaBH4, HgSO4, these are the chemicals you can use. Dilute H2SO4, concentrated H2SO4, PCl5, magnesium, ether. Now students, I told you, we are using what do you call it, Grignard's reagent. We can use aldol condensation sometimes to lengthen the reaction, lengthen the molecule, or Grignard's. Aldol requires sodium hydroxide. We don't have sodium hydroxide here, right? So definitely not aldol. Magnesium and ether is there. Good. So that means what? We can use yes, magnesium and dry ether. Okay, sorry, dry ether. But even if they have given ether, you can use it. Keep in mind, only lithium aluminum hydride cannot be reacted in the presence of water. Sodium borohydride can react in the presence of methanol or water, right? So that is not a problem. Right, I think that's enough time, because since everything is mentioned to you here, that I have helped you out a little bit here, we can get to the answers now. Now seemingly it looks like, let's say, as soon as you look at it, some of you might feel this is a bit of a difficult one, right? Some of you might feel it's a bit of a difficult question. Let's see if it is actually difficult. So we are starting with CH3, this compound, and we are asked to produce this CH3, bear with me, looks a bit odd if I write it that way, CH3, CH3, CH3 here and CH3 here. Now listen, pay attention. Now always identify the fact that carbon chains length have increased, or the number of carbon atoms in the molecule have increased. How can we do this? Like by observing the reactants that are there, we can figure out Mg ether is there. Sometimes they misguide you also, right? Sometimes they won't directly give you an easy hint. But we know carbon chains length can be increased only in few ways. Out of those, most popular are aldol or self-condensation, and the next one is we have magnesium diether, or in other words, Greenhouse reagent. There are other ways, like for example, alkyl halide related reactions can also increase the length of the carbon chain. But the popular ones are Greenhouse and self-condensation usually. So we do have the reagents needed to form Greenhouse reagent. Now we know when Greenhouse reagent is used, aldehyde or a ketone is going to be reacting with Greenhouse, and then while we add them together, there is a OH group produced, right? And then we can easily remove this OH group by doing what? Heating with acid. Then the OH group will be leaving, forming a double bond. Is that clear? So this could very well be a situation like that, right? So there's a double bond here. So we understand first of all Greenhouse, that's the first step. I'm trying to tell you how to approach this question. Don't just listen to it as a story. Approach this question the following way. Double bond here, and the number of carbon is twice as many carbons here, so this must be Greenhouse, and you can't bring any other organic compound, right? So that means if you are doing Greenhouse, we need to have certain two molecules, and you need to produce certain two molecules from here. First of all, figure out what molecules are there. Now before coming to this point, we know there would have been a molecule where there is a carbon oxygen where there was a OH group. So there is CH3 here. I will write them here, CH3, and then again also CH3 here. There would have been a hydrogen, and this one would have been a OH. When they leave only, you produce this. Am I correct? Right. So that means this would have been, this section would have been a ketone, because that's why it is producing a OH group there. This would have been connected to a Greenhouse reagent. Is that clear? So for example, if you visualize it, you'll be able to see this was produced using something like CH3. I will write it in a way that you see it, right? Like this. CH3. Let's write like this. Okay? Do you understand? So this section was a ketone, and when the Greenhouse reagent attacked, this part became OH, right? So the Greenhouse reagent would have been something that had this section, and here would have been the MgBr part, because we know Greenhouse is like a carrier. It takes a certain group and attach it to the carbonyl carbon and leaves, right? So that means this section would have been directly connected to MgBr or MgCl, whatever, right? So here this section would have been something like this. There's a hydrogen here, so we'll call it CH, and then this bond would have been connected to Mg. In this case, we haven't been given anything containing bromine, so that means we would have used a Cl. So actually it's MgCl. We didn't have any HBr given here, no? Or no PbR3 also, so that means we would have had to use PCl5. So we can form a greenhouse reagent using this as well. Any alkyl halide reacted with magnesium in dry ether will produce a greenhouse reagent. So do you understand now? We are working backwards, okay? It's easier that way, right? Do you understand that we can take this and then react with, like, one another to form this? Right? Actually, we can show two steps. This react with this will form, like, something, and then after that, if you add H plus water, you will produce a final product. Is that clear? So that is what we need to do. So I will erase these parts again because I want to show you the two-step process of my MgCl reacting with one another, MgCl and ketone reacting with one another. I want to show it separately. So I will write the process from here in two steps later on. So I will erase this part. But now we have an understanding what we need to form. We need to have a ketone, and to produce this, we would need something like this, CHCl. We need something like this. So basically, we need an alkyl halide with a chlorine in the middle. Alkyl halide with a chlorine in the middle is needed. Is it understood? Alkyl halide with a chlorine in the middle is needed. And then what else? Yeah, that's it. After that, we can continue on forming the final product. So how do you produce this and how do you produce this is what we need to know. So now producing this is the simplest one actually. You can see if you take the given reagents, do you see how we can produce the ketone easily, students? Can someone please tell me how can we produce ketone easily? HgSO4, very good, and dilute sulfuric. Normally we write Hg2 plus and dilute sulfuric, no? Right? So HgSO4 has Hg2 plus, no? HgSO4 has Hg2 plus. So therefore we write HgSO4 and dilute sulfuric. Now this will produce our what do you call it? Our ketone. Done. So I will erase these parts. Now I need to produce a alkyl halide. I will do the process nicely. Now this is the thinking process earlier. Now we are actually doing it. So the next one is we are trying to produce a what do you call it? We are trying to produce an alkyl halide with a Cl group in the middle. So how can we do that? With the ones that are given here, actually I don't have to start from here again and do it. I can actually do something from here onwards. Can you tell me how can I get a Cl here? Using everything that we have here? It's easy. Sodium borohydride, right? Sodium borohydride can be used, right? So what else do you need? Water. So instead of water, we can use dilute H2SO4, right? Because dilute H2SO4, when it comes to lithium aluminum hydride also, I don't know whether you remember in the second step what we wrote was water, but water was written as H plus H2O, right? It has to have a little bit of H plus in it, right? So we can write here, if you react this with NaBH4 and dilute H2SO4, then we are actually going to end up having so it's a ketone. Ketones when reduced produces secondary alcohols. Secondary alcohol can easily be turned into secondary alcohol can easily be turned into secondary alkyl halide by the addition of PCl5. PCl5, so Cl here. And now from here onwards we can add magnesium in dry ether. So you form CH3, CH, CH3, and then here MgCl. So that is our Greenhouse reagent. That is our Greenhouse reagent. So you can now bring the Greenhouse reagent and this together, this and Greenhouse reagent together. We can say Greenhouse reagent is reacted with this. We can even show that we are reacting them together. Sorry, not here actually. We need to show the arrows. And you need to add dry ether here also. Dry ether will produce CH3. Now this carbon will be getting added with the section that is present here. CH3, COH, right? And I will write this carbon CH3 group here. And the rest of the molecule, this part, is going to be written like this. C, CH3, CH3, right? Oh, sorry, CH, CH3. Now this part is there. So actually I just added dry ether. I didn't add anything else. So this has to be MgCl. I only added dry ether. No? I didn't add water. So if you add dilute H2SO4 in place of water, then quickly this will leave and will form this CH3, CH3, OH, and then if you add concentrated or normal sulfuric and heat, anyway this double bond will be formed. So concentrated H2SO4 and heat it, a dehydration reaction will take place. Concentrated H2SO4 and you can heat it, you can see a dehydration reaction taking place. Is that clear? They have given concentrated H2SO4 instead of aluminium oxide, they have given that. So that is how you do this reaction. So in the conversions when you do at the exam, try to do the Greenhouse reagent parts in 2 steps. Otherwise it might not be very clear. I could have written 1 dry ether, 2 dilute sulfuric, but when you do it this way, it's very clear that you have a good understanding of what's going on here. It's very clear that you have a good understanding. Any questions about this? All good? So we have to do a few more questions from these parts actually, and we need to make sure that we do many questions from other parts as well. So I will prioritize first of all finishing off the lesson. The lesson has only 2 more parts: carboxylic acids and the nitrogen containing compounds. Nitrogen containing compounds are very basic, so we talk about mainly amines, under that also only primary amines. After that we come to amides, and here we don't go into details about amides. Is that clear? So we mainly learn about primary amines, right? And the reactions revolving around primary amines, and that's it. So carboxylic acids have few reactions. They are derivatives like SI chlorides and esters are also going to be discussed, but we can finish it off
actually these two parts can be finished off into classes. If you can have next week, I want to start something. So next week, no issues, no barriers, nothing. So tomorrow they are closed actually. So this they couldn't give. So we will have next week no issues. We'll have from morning onwards, right? So I want to finish the lessons off. I'll do questions as I do now, right? So we'll do the 2 sessions together. Organic chemistry theory will be finished then, and we'll be doing questions. If I have the time to finish questions next week, we'll be finishing questions as well. Is that clear? So from there onwards, it's going to be proper paper class from the next week. So paper class in the morning, afternoon, theory class. So since tomorrow next week is a theory class, can you please somehow come, right? Somehow try to be there. Either way, I'll give you the recording, but if you can, please be here. So tomorrow, next week, we'll discuss the times. What time can you be here? We can finish early if you are here early. So let's say 9 to 10, 11, 12, 1. 9 to 1 we'll have one class. How much of a break do you want in the middle? 1 hour is enough, right, to eat? Right? Why we need a bigger break? You have another thing happening next week, all right? 1 hour break, right? Depending on how tired you are, I'll give you 1 hour break or maybe 1.5 hour break, and then from there onwards 2 to 6 we'll have the class, right? So we can start early, finish early, right? So we'll go ahead with that program. So that will be all for today, everyone. So next week we will be having that additional class I spoke to you about, right? Any questions? Right? So this is like, all right, bear with me. So I'll see you all again next week then, right? See you guys. What question? A and B are octahedral. Bear with me a second, I'll turn that off and come. Right.